Hello friends, I welcome you in lecture number 13 on complex integration. So far we have seen how we can evaluate contour integrals or complex line integrals, and we have seen that we are converting our complex line integral from two variables, say x and y, to a single variable, and in which our variable is some parameter, say t, and our complex line integral is converted into integral of real function or real integral, and then we can evaluate easily. So that was one method of evaluating contour integrals. We convert our function f of z from two variables x and y to a single variable, and then accordingly we convert our complex line integral into real integral. So that is the first part, or we can say that is the first method for evaluation of complex line integrals or contour integrals. And in that method we have seen that suppose we have 2 points, say z1 and z2 in the complex plane, and suppose we are integrating along say contour c1 from z1 to z2, and suppose we change the path of integration. Suppose we consider another path or another contour between z1 and z2, then we have seen that these two integrals are different. That is, the contour integral depends on the path of integration between 2 points, but sometimes for special type of functions, if we integrate along any path between 2 points, then we get the same answer. So for certain class of functions, this contour integral becomes path independent. So we are going to discuss those type of functions, and in which cases we can say that line integral is independent of path between 2 points in the complex plane. So that we are going to discuss in this lecture. We are going to discuss path independence of complex line integral. We are going to discuss that under which conditions we can say that line integral of function f of z between 2 points z1 and z2 is same along any contour or any path from z1 to z2. That we are going to discuss in this lecture. Before starting this path independence of line integral, we have to understand one definition, which is simply connected domain. We will just understand what is meaning of simply connected domain, because we require this definition in understanding of path independence of line integrals. So simply connected domain is domain in the complex plane or some region in the complex plane in which if we take any simple closed contour, then that closed contour contains only points of that domain. For example, suppose I consider this square in the complex plane. Suppose this is square with these 4 points in the complex plane. Then I want to check whether this is simply connected domain or not. So what I will require, if I take any simple closed contour. Now we are familiar with closed contour and simple closed contour. Closed contour means that contour whose initial and starting endpoints are same, and it is simple if it does not cross itself. If I am considering this contour, then this is closed, but it is not simple because it intersects itself at this point. But this contour is simple closed contour. This we have discussed in lecture number 1 on contour integrals. So this square is simply connected domain if I take any simple closed contour in this square, then the points inside this simple closed contour are points of this square only. So here we can see that if we take any simple closed contour inside this square, then the points which are interior to that contour are points of this square only. Therefore, this square is an example of simply connected domain. Similarly, if we take any circle in the complex plane, for example, suppose I consider any circle in the complex plane, then it is simply connected domain, because if I take any contour inside this circle, then all the points interior to this simple closed contour are points inside this circle. So interior of any circle, if we consider interior part of any circle, then that is simply connected domain, or interior of any circle is called open disk. So open disk in the complex plane is always simply connected domain, because if we take any simple closed contour inside this circle, then the points interior to that simple closed contour are points of this open disk only. But suppose I consider the area between two circles, that is annular domain. Suppose these are two circles and I am interested in the area between two circles, then this is not simply connected domain, because suppose I consider this simple closed contour which is in the annular domain, or which is between the two circles, then you can see the interior portion of this simple closed contour contains those points which are not in the annular domain. So this annular domain is not simply connected domain, because if I take this simple closed contour, then the points interior to this simple closed contour, all the points are not the points of this annular region. So whenever we consider annular region, that is region between two circles, then it is not simply connected domain, because you can see that here we have found one simple closed contour and all the points inside this simple closed contour are not the points of annular region. There are some points which are here and these points are not in this annular region. So this is not simply connected domain. So I hope now it is clear what is meaning of simply connected domain. Any domain is simply connected if we take any simple closed contour in that domain, then that simple closed contour contains only points of that domain. We can have another example also. This is another example of simply connected domain. Here if I take any simple closed contour inside this, then the interior of this simple closed contour contains only points of this. Similarly, if we consider whole complex plane, then that is always simply connected domain, because if we take any simple closed contour in the complex plane, then it encloses only points of D. So we can understand simply connected domain in this way also, that domain in which there are no holes. For example, if I consider this annular region between these two circles, then we can see that there is a hole in this domain, therefore it is not simply connected domain. So for example, another example is this one. This is not simply connected domain because it contains one hole. So this is meaning of simply connected domain. Sometimes they can ask you to write down the definition also. A domain D in the complex plane is called simply connected if every simple closed contour in D encloses only points of D. That means if we take any simple closed contour in a domain D, then the points which are inside that contour are points of given domain, D only, and that must be true for every simple closed contour. Now where we require this definition? So we require this definition in one result. Suppose we have a simply connected domain. Suppose D is simply connected domain, and suppose we consider one function, say f of z, and this function is analytic in this simply connected domain D. Again I repeat, capital D is simply connected domain, and we have a function f of z which is analytic at every point in this simply connected domain. Then our result says that if f of z is analytic in a simply connected domain, then there exists an analytic function denoted by f of z such that if we take derivative of this capital F of z, then we have this f of z, and if we want to integrate this f of z along any path between 2 points z1 and z2 in this domain D, suppose we have this domain D is simply connected domain, I consider 2 points z1 and z2 in this domain D, f of z is analytic at every point in this simply connected domain, then there exists an analytic function f of z whose derivative is given small f of z, and integral of this f of z between 2 points z1 and z2 in domain D is equal to value of this capital F of z at z2 minus value of capital F of z at z1, and this is the value of line integral of f of z along any path between these 2 points. So it becomes independent of path. I can have infinite number of paths joining z1 and z2, and all those paths must be inside this simply connected domain. So if f of z is analytic in a simply connected domain, then there exists an analytic function capital F of z such that derivative of capital F of z is small f of z, and integral of f of z along any path from z1 and to z2 is given by f of z2 minus f of z1, and this is very nice result. And whenever we have analytic function in a simply connected domain, then we don't have to apply that earlier method. We can directly find out value of integral of f of z simply by finding value of this capital F of z at end points of the integral and then taking their difference. So this is similar to the fundamental theorem of calculus, and we can consider this as fundamental theorem of complex analysis also. Here we require that our function is analytic. So you have seen earlier lectures, and you have seen that the functions which we have taken in the problems up to this lecture were z bar mod z square e to the power pi into z bar 1 over z minus z0. All these functions we have taken in earlier lectures, and we know that z bar is nowhere analytic, mod z square is also nowhere analytic, this is nowhere analytic, this is analytic at every point except z0. So the problems which we have taken up to lecture number 12, in those problems we have taken those functions which are not analytic. But suppose I want to integrate z square in the complex plane along some contour, then I can use that earlier method. But now I know this result, that if my function is analytic in a simply connected domain, then I can use this result and I can easily find out integral of analytic function without using that earlier method. That method is applicable to functions which are analytic as well as not analytic, but this is shortcut. Whenever we have our function which is analytic in a simply connected domain, then we can use this result. So I have written this result systematically here. I have written that let f of z be analytic in a simply connected domain D, then there exists an analytic function denoted by capital F of z such that capital F dash z equal to f of z at every point in domain D, and for all paths in D joining 2 points z1 and z2 in D, integral of f of z is given by f of z2 minus f of z1, and this function capital F of z is called an antiderivative of f of z in domain D. We have seen in earlier lectures on complex differentiation that z square is analytic at every point in the complex plane, and if we consider f of z equal to say z cube by 3, then derivative of f dash z is going to be 1 by 3 into 3z square, that is z square. So because we know that z square is analytic everywhere in the complex plane, and we know that complex plane is a simply connected domain, therefore we have this function which is antiderivative of this function. So we can write integral of z square along any 2 points, along any path joining any 2 points in the complex plane. This we can directly find by considering this value of z cube by 3 at z1 and z2. So first we will put z equal to z2 and minus z equal to z1. So this is similar to the integration which we study in calculus or real analysis, but this here I can apply this result because I know that z square is analytic everywhere in the complex plane. So if I am given any path between 2 points, then I will simply put z equal to z2 and z equal to z1 in the antiderivative of z square. So whenever you have example of contour integral, you check whether your function is analytic in a simply connected domain, and if that happens, then you can apply this result which we consider as indefinite integration of analytic functions. But this is applicable whenever we have an analytic function in a simply connected domain. So I have taken one example here. Evaluate integral of z square along contour C, where C is the straight line from 0 to 1 plus I. So here I have, suppose this is z equal to 0 and this much distance is 1. So this is 1 plus I, and C is the straight line between these 2 points. Let me clear this. So I have this type of situation. So I want to integrate along this line segment from 0 to 1 plus I, and I know that this z square function is analytic everywhere. So I will consider whole complex plane as the simply connected domain, and I can apply that result. So here I don't have to write down the parametric representation of straight line joining 0 and 1 plus I, and then I have to convert z square in the form of parameter. So you can do in that way also, you will get the same answer. But here I know that z square is analytic everywhere in the complex plane. So we can write that we know that, suppose we denote z square by f of z equal to z square is analytic everywhere or analytic in the complex plane or in the xy plane, and complex plane is simply connected domain. So here we mention that which is simply connected domain. because I want to apply that result. Therefore, I require that our function is analytic in a simply connected domain. And if we consider capital F of z equal to z cube by 3, then we know that this derivative of capital F of z is 1 by 3 into derivative of z cube is 3z square, that is z square, and this is equal to f of z for all z in the complex plane. So this capital F of z is an antiderivative of f of z equal to z square. So therefore integral of f of z from z equal to 0 to 1 plus I equal to value of capital F of z at 1 plus I minus value of capital F of z at 0, and f of z is z cube by 3. So here I will put z equal to 1 plus I, f of z is z cube by 3, so 1 plus I cube by 3 minus f of 0, that is z equal to 0, and here I have to simplify this. This I can rewrite as 1 plus I times square of 1 plus I divided by 3, and then I have 1 plus I. If I expand this, I will have 1 plus 2I plus I square divided by 3, and because I square is minus 1, we have to cancel these 2, and I have 2I into 1 plus I divided by 3, or this I can rewrite as 2I plus 2I square divided by 3, and because I square is minus 1, this is minus 2 plus 2I divided by 3, or I can rewrite this as 2 by 3 into I minus 1. So this is integral of z square from 0 to 1 plus I. So this is integral of z square along the straight line from 0 to 1 plus I, but if we are given another path from 0 to 1 plus I, then also we will get the same answer. Suppose we are asked to find out integral of z square along any path from 0 to 1 plus I, then also we will get the same answer, which is 2 by 3 times I minus 1, because z square is analytic in a simply connected domain which is complex plane. So this is another way of evaluating contour integrals whenever we have an analytic function in a simply connected domain. So I stop here, and we will continue with this type of problems in next lecture. Thanks for watching.